Hello everyone. We're going to discuss section 11.3, solubility. The learning objectives for this section: describe the effects of temperature and pressure on solubility, state Henry's law and use it um, in calculations involving the solubility of a gas in a liquid. We're not going to be doing the calculations here, but you want to be able to understand qualitatively the applications of that law. So a little bit of a modification to the learning objective in your book. And then explain the degrees of solubility possible for liquid-liquid solutions. So we've talked a little bit about solubility before, but I want to start out by discussing some definitions here. Solubility is how much you can have in solution. So it's the maximum concentration in order that you can have in a solution at equilibrium. Okay, so the key there is it's at equilibrium. So when it's at equilibrium, you have that going back and forth from dissolved to undissolved. Typically, when we have something that is at the limit of solubility, we call that a saturated solution. So we have as much of the solute dissolved in the solvent as possible. Sometimes what that will look like is you'll have, if it's a solid and liquid solution, you'll have some extra solid left on the bottom, and that way we know if any more of it could dissolve, it would dissolve. If something is below the solubility limit, we say it is unsaturated. So we could potentially get more of that solute to dissolve in the solvent. It is actually possible to have something that is supersaturated. And you might wonder, well, why is that possible? Why don't we just, up the limit of solubility to whatever that is? That is because this is a non-equilibrium state. And again, we'll get into that in more in Chemistry 1B in terms of equilibrium, but it is possible to kind of go beyond what you technically are supposed to by having a very careful process. It's kind of like stacking little blocks. They're stacking like a stack of cards. It's unstable. It will probably fall down at some point. So that's what a supersaturated solution is. And when you have these, what will often happen is a little tiny disturbance will cause a massive amount of solute leaving the solution. So let's get into some specifics. And how this is going to work, we're going to go through each of the states of gas, liquid, solid in terms of the physical state of the solute, and then discuss how those behave in a liquid solution. So the solutions we'll be looking at here will always be liquid phase, but the solutes will be all three of the physical states. Okay, so let's look at gas phase first. So in order for a gas to dissolve in a liquid solution, there has to be some amount of intermolecular forces between the gas molecules and the molecules of the liquid solvent. So anything that is sort of getting away from those attractions is going to lead to a lower solubility, whereas anything that is kind of moving in the direction of those attractive forces is going to lead to a higher solubility. It discusses here a little bit at the start the effect of intermolecular forces, and we've talked about that a bit already in terms of the like dissolves like concept. So things that are basically nonpolar are not going to dissolve as well as things that are somewhat polar or at least are more polarizable. So something like helium, for example, is very difficult to dissolve in a liquid, whereas other gases will be somewhat easier, although the amount that does dissolve is often very small. In terms of that tension between kinetic energy and intermolecular forces, we would definitely expect, if we have more kinetic energy for a gas, it would probably be less likely to stay in solution. Because for a gas molecule, what that looks like is that the more kinetic energy it has, the more ability it has to escape the intermolecular forces and then become a gas molecule, which is not even around um, the solution anymore to be dissolved in it. And so that's what we see here in terms of, if you look at these different gases, you'll see that as you increase the temperature, their solubility tends to decrease. And you can see they don't always, decrease by the same amount, but we have a decrease in solubility as we increase the temperature. The idea there again is that as the temperature gets larger, you're tending to escape the intermolecular forces, similar to, say, a vaporization. It's not the same thing as vaporization, but it's similar in terms of, as you increase temperature, you're going from a condensed phase in terms of a solution towards a gas phase where there are no effective intermolecular forces. Okay, so that's one of the major trends here, is that as you increase temperature, you will have an increase in solubility. Actually, let me go ahead and highlight this. And your book is stating it in the reverse way. So gas solubility typically decreases as temperature increases. So kind of flipping around, where I was focusing on temperature, is focusing here on solubility. But the same idea. There are some definite effects on this. So we can see, with increased temperatures, in terms of the temperature in a location, less things like oxygen dissolved in the water, which will affect the health of the fish. In fact, if you are somebody who enjoys fishing, you might find that you catch more fish in shady spots, and that's because there's more oxygen there. So they're going to where the oxygen is. So hopefully we can keep the temperatures low enough that the oxygen will stay in the water, enough to support the health of the life that lives there. Another thing that affects solubility is the pressure of the gas, and it's not the pressure of all gases; it's the partial pressure of the particular gas that you're trying to dissolve in the solution. A great example of where we see this applied is in any carbonated beverage. So they often come in containers, and when you open the container, you hear a hissing sound, and that hissing sound is the pressure that's being released from the container. Usually, I think they have a pressure of around 2 atmospheres, and so you're releasing some of that, and that pressure is often comprised completely of carbon dioxide. So in the atmosphere, carbon dioxide is about 0.04%, whereas in the container, it is 2 atmospheres. So we're looking at a very big difference in the concentration between what's inside the container and what's outside the container for the carbon dioxide. And so what you'll often notice is that as you look at that carbonated beverage, once you open the container, it starts to form bubbles, and those bubbles are the carbon dioxide escaping the solution, and we're showing a picture of that here. And we often refer to this as going flat. So the carbonated beverage has gone flat when all of those carbon dioxide molecules have left the solution. So we can describe this relationship, and it's actually it's actually one we can describe mathematically, because it is that exact. And we're showing that here with Henry's law. We're not going to do a calculation with this, but just be aware of the trend in terms of how partial pressure and solubility go together. And so we're stating that here. So the quantity of an ideal gas that dissolves in a definite volume of liquid is directly proportional to the pressure of the gas. So as the pressure of the gas increases, the solubility of it within the solution will also increase. And that's what this is saying. We're not going to do, for the exam, a calculation with this, but you do want to qualitatively be able to describe that relationship. You might have a homework question about that, but it won't be on the exam. Let's go ahead and there's some interesting applications in some of these questions in terms of thermal pollution, and then the bends, which is something that can happen if you get nitrogen into your blood because of a high pressure by going underwater. Henry's law is not perfect, so there are places where it doesn't always apply, so just be aware of that. And then there's some other examples here in terms of there was a large death that occurred in Cameroon because of a lake that had a lot of carbon dioxide dissolved in it. So they had to come up with a way of mitigating that. So there's a discussion of that here. So let's talk about liquid solutions. There are different possible ways that we can mix liquids together and different results. So one possibility is that if you can mix liquids in any proportion and you end up with a solution, we say that they are miscible. Okay, so miscible means that any amount of the liquids mixed together will form a solution. So ethanol water is a kind of famous example of a miscible solution of liquids, in that you don't ever have a separation occur, which is why there are some very high alcohol content beverages available. The other possibility is if they are, well, let's talk about miscible a little bit more. For miscible liquids, they have very similar polarities. So with ethanol water, for example, they both have hydrogen bonding. So because of the hydrogen bonding, they are always going to fit well together. There are also some nonpolar liquids that would be miscible with each other. So any amount of them mixed together would form a solution. And we're not going to get into those because they're not something that you would necessarily know what chemicals I'm talking about. But the idea there is the more similar they are, the more likely they are to form lots of able to form solutions over a wide range of over the entire spectrum of concentration ranges, I should say. If they do not mix very well, we say that they are immiscible. And so what that means is they form separate layers, and you have a little bit dissolved in each layer. So what an example of this that you're probably familiar with is oil and water. And if you are at a gas station on a rainy day, you'll notice that there are some colorations on the top of the water puddles, and that is the gasoline spills floating on top of the water. They don't mix together very well. There is some amount of the gasoline dissolved in that water and some amount of the water dissolved in that gasoline, but it's not very much. So they form layers, and we say that they're immiscible because there's a very small, very low amount of each liquid dissolved in the other one. Here we're showing an oil-water mixture, and this is also comes up with some salad dressings where you have vinegar and oil, and you have to shake it before you you put it on your salad, or else you'll get either just oil or just vinegar. Sometimes the word partially miscible is used to indicate that there is a significant amount that dissolves, but you're still going to end up with layers. So we can see that here, where we've got bromine and water, and the coloration there is from the bromine dissolved in the water, and this is bromine liquid just by itself. So they are what we might say partially miscible, but they don't completely mix together. So that's how we discuss liquid-liquid solutions. And then finally, we have solid in liquid solutions. And the main thing we'll talk about here is temperature. So it turns out pressure does not have the same effect with the solid as it does with the gas. And you can think back to our phase diagrams to kind of see how, okay, the gas phase is where something like pressure can have a larger effect. But it does have an effect on, but temperature does have an effect on solubility. Here we're showing what that often looks like. So we're showing a number of solids dissolved in water, and you can see a trend that for most of these, as you increase the temperature, you are increasing the solubility. There are some exceptions, right? So there are some exceptions, and then we also see that for some of them, it's a much more pronounced trend. So for potassium nitrate, for example, compared to sodium chloride. Sodium chloride doesn't change that much, potassium nitrate does. Sugar, you can also see, has a pretty pronounced trend. And for anyone who has done any cooking with sugars, you kind of probably know that as well. So this is the opposite of the trend that we see with gases dissolved in a liquid solution. And the reason for this is because there's something else going on. So for a solid, if a solid escape solution is not going off into the atmosphere, it's going to probably fall to the bottom of the solution. So it's kind of still around, and it's still subject to those intermolecular forces. So it's not something where if you increase the temperature, it can overcome those intermolecular forces. It still has intermolecular forces within the solid itself, right, between particles of the solid. So what's going on here is actually the mixing effect. So it turns out, and this again something we'll get into more detail on in chemistry 1B, that the effect of mixing is more pronounced at higher temperatures in terms of stability. So this is related to that concept of entropy that you'll be discussing in chemistry 1B. So the higher the temperature, typically the more of an effect from mixing things around. And so when you have a solution, you're mixing things around compared to having two pure substances. So it's more stable to have more mixing at higher temperatures. So that's why we see this trend for solids. So that's a little bit theoretical, I guess, at this point, because we haven't gotten into entropy yet. So what I would say is, for this one, you might just remember that you get more sugar dissolved as you increase the temperature without really getting into the why as much, and maybe use the why to describe some of the gas phase properties, which are, I think, more intuitive in terms of why they're true. But for this module, essentially what you'll want to know is the trends associated with solubility for different types of solutes dissolved in liquid-phase solutions, so gas, liquid, or solid.